Hello and welcome to the 11th lecture, overall MD review and scope. So we have been discussing about molecular dynamics theory for the previous several lectures. And in the immediate earlier lecture, we have actually discussed about energy minimization. And in this lecture, we will just get a review of MD and its scope. So in energy minimization, we have said that we want to run an MD simulation, but before that, we have to actually minimize the total potential energy of the system by running some algorithms by this general scheme, by setting up some energy tolerance and force tolerance and running it for some iterations to find whether after some iterations the energy and displacement is close to zero, so that we can be sure that the current conformation is energetically viable to run an MD simulation. So now, as I have introduced so many concepts to you in the previous several lectures, now I think that it will be very helpful to get a review of what you have learned so far in terms of molecular dynamics theory and scope. So let me give you a flashback that MD simulation means solving the force F equal to ME equation, and we want to determine the trajectory of the atoms through this atomistic model by solving this equation continuously after several time steps over and over again. And then we analyze the data and output results, whether it be force, displacement, or stress, strain, or something like that. So in terms of scope of MD, what we can and can't do, we can solve problems which includes microseconds of simulation and systems that is nanometers of length. And we use some force fields that are approximated, not parameterized particularly for our system. So we may have to do some tweaking according to our system. And sometimes it's not possible for some particular problems. And it's computationally expensive, especially if you run for several microseconds, or if you run for a very large system. It will cost you hours and a lot of money, because the high performance computational units are generally purchased by your institution. And sometimes your insight that you are getting by running the molecular dynamics simulation, it might not be relevant to your system. It might not be even needed. And sometimes you get partial insight because your problem may need some electrical, optical, or magnetic property insight, but you are not getting it from MD simulation. So MD simulation, long story short, MD simulation is not just the only answer to all the questions according to your research. You have to find out whether MD simulation is the particularly appropriate approach to solve your research problem. But we can definitely solve a lot of mechanical, structural, biochemical, or thermal problems, and we can get particular insights at atomistic level by using this particular method or tool. So that's why we use MD. And if we want to pose it in terms of biomechanical or chemo-mechanical problem, we can solve these type of research questions, like whether in a simulation, whether a particular protein-to-protein interaction is getting affected, whether we can determine the atomistic level of deformation by using computational mechanics principles, or we can get a lot of atomistic level of insight. But if your system is too big, we'll probably have to leave atomistic approach to solve a problem and go to continuum level of modeling or experimental approach if it's appropriate. So it's very important to really think through your problem to find out the most appropriate solution to solve your problem. So from the next lecture, it will get more interesting, I think, because we will introduce you to the concept of MD software. Like we have learned about how MD simulations theoretically works, what goes on under the hood, but now you will know what software or what packages to use to run a particular MD simulation. So I will see you in the next lecture. Thanks.